Welcome to my second example on how to calculate bending moment and shear force in a simply supported beam. In this example, we've got a 8 meter long beam with three different types of loads on it. So we've got a 3 kilonewton meter line load, we've got a 2 kilonewton meter bending moment located 4 meters along the beam, and located 7 meters along the beam, we've got a 5 kilonewton point load. So we know this beam simply supported. There's three reactions. So we're going to have, well, we'll call this side A. A, we've got reaction AY, and B, we've got reaction BY, and we also have a horizontal reaction at A, which will be known as AX. So this beam's in equilibrium because it's one member and we have three reactions in total. So we know that sum of our reaction forces is equal to 0. So if we set up our axis, so anything in the up direction and from left to right is positive, and any bending moments we have going clockwise are also positive. So first of all, we want to find out what our reactions are. That's going to be our first step. So step one is reactions. Spelt less messy. So if we take the sum of our forces in the x-axis, because our beam's in equilibrium, we know it's equal to 0. So therefore, AX equals 0, as there's no horizontal forces. If we take our sum of forces in the vertical axis, in the y-axis, that's also going to be equal to 0. So pushing upwards positively, we've got AY, we've got reaction BY, and that's it in the positive axis. So in the vertical axis, pushing down, we've got this 3 kilonewton meter line load acting over 2 meters, so that's going to be 6 kilonewtons. So we're going to have minus 6 kilonewtons. And the bending moment doesn't affect us, and we've also got this 5 kilonewtons acting over there on the right hand side, and that's equal to 0. So we now have AY plus BY equals 11 kilonewtons. So we're going to want to find either A or B y. We're going to try and find by, and we can do this by taking the sum of moments at point A. Because we know that this is a pin connection at A, we know that the sum of the moments at A are going to be equal to 0. So when we write out this equation, we can rearrange it and hopefully find by. So if we're looking at point A, what do we have? So we've got a 3 kilonewton line load acting over 2 meters, giving us our 6 kilonewton line load, 6 kilonewton point load, and that's acting at the halfway point of the line load. It's acting 1 meter away from the support. So that's going to be 6 kilonewtons times 1 meters, put that in brackets, and that is pushing us around clockwise, so that's going to be positive. We then also have 2 kilonewton meters acting 4 meters away, but this is just going to be 2 kilonewton meters because it's already a moment. And then we've got our 5 kilonewtons, which is acting 7 meters away, so, and that's also going to be clockwise, times 7 meters. And then we've got by, which is going to be pushing up. Let me just, it's missing there. And that's going to be pushing around anti-clockwise in the other direction. So that's by, and the lever arm from A is 8 meters. And that is all equaled out to 0. So if we rearrange this, we're going to have 8by equals 6 plus is 8, and then I'm going to need a calculator. Sorry. 2 plus 5 times 7 is, helpful if my calculator was turned on, 43 kilonewton meters, and that, therefore, send that along, by equals 5.375 kilonewtons. And if we sub that back into equation 1 here, we know AY, scroll up a little bit, equals 11 kilonewtons, take away 5.375. These units are going to be a nightmare, I can already tell. 5.625 kilonewtons. Okay, so we've got our reactions, our vertical reactions that are supports. I'm going to go ahead and redraw this with our reactions, and I will get back to you shortly. We've got our beam all drawn up with our reactions added. The next step of the video is to calculate the shear force. So that's step 2 is shear force diagram. Okay, so I, like a lot of others, like to set up a little grid system and put vertical lines at points of interest. So a point of interest typically occurs at your supports, where you have a concentrated load, maybe a bending moment, or where you have a line load. So we've got a point of interest here, got a point of interest where our bending moment is, and we've also got a point of interest where our point load is. And then a beam, and this is going to be the positive, and this is going to be negative, and this is 0, and we're going to work from left and go right with our shear force diagram, and everything here is going to be in kilonewtons. So, starting at this end, left hand support A, we're going to be pushed up because we've got a positive reaction. If I just also draw this here to remind us of directions. So we're going to be pushed up, and this is going to take us up at an increment of 5.625, nice and rounded. So here, and this is 5.625 with a dot. As we move from our first point across to our second point of interest, we know we've got a 3 kilonewton meter line load which is pushing downwards. So this is going to send us linearly down at an angle of 3 kilonewtons per meter, well, a gradient of 3 kilonewtons per meter. So that 3 kilonewtons per meter is acting across 2 meters, that's a total of 6 kilonewtons. So that's how much our shear force is going to reduce by. So that's going to send us just into the negative axis about here. And that reduction from up here down to this point here is going to be minus 6. And that's going to bring us to 0.375, negative 0.75 kilonewtons. So moving from point 2 to point 3, nothing's actually happening. So we've got no additional forces, so our line is just going to be, and moving from point 3, 4, we also don't have any additional forces. This bending moment won't affect our shear force, so it's just going to carry on moving along steady at 0.375 until we get to 5 kilonewton reaction. So we're now at a 5 kilonewton reaction at point 4, and this is actually going to knock us down another minus 5 kilonewtons. It's going to take us down minus 5, and that will bring us down to here, and that is going to be minus 5.375. And then between point 4 and point 5, we actually have no forces on our beam again, so our shear force diagram is just going to stay plateau, flat. And when we hit our support, we've got a 5.375 kilonewton force pushing us back up, so that's going to make us jump up positive 5.375, and that brings us back up to 0. So this is what our shear force diagram looks like. We have a point of interest here which will be useful for our bending moment diagram, where our shear force crosses the 0 axis. This means in our bending moment diagram, at this point we're going to have a peak in our bending moment force. So we actually need to calculate the length, or the distance this is happening from our support A. So that's distance x. And we can calculate this quite easily because we know that the total drop is 5.625 kilonewtons, and it's acting and it's reducing at a rate of 3 kilonewtons per meter. So x equals 5.625 kilonewtons divided by 3 kilonewtons per meter. If I put that into a calculator, 625 divided by 3 gives us 1.875 meters. Okay, so that's all for this. I'm going to quickly draw up everything we need for the bending moment diagram, and we'll move on to that next. Okay, so I've got our grid all set up for our bending moment diagram, and as you can see, we've got 1, 2, 3, 4, 5, 6 points of interest. We've got an additional one to last time, as mentioned before, because we've got this point of interest here where our shear force diagram crosses the 0 axis. So we're going to work from left to right as before. It's going to be our bending moment diagram, and everything in this is going to be kilonewton meters. That's our unit. So let's start at M1. So we know this is going to be easy. This is going to be 0 because it's a pinned support and no moments act pinned support. Now we want to know whether or not our bending moment diagram is going to increase or not. Because our shear force diagram is in the positive, we know that we're going to have an increase in bending moment diagram. And because our line is linear in our shear force diagram, we're actually going to have a parabolic line in our bending moment diagram, and that's going to reach point 2. And at point 2, we know we're going to have an apex because it crosses 0. Crosses the 0 axis in the shear force diagram, so we're going to have a peak, and that's going to flatten out and come from down there. So we want to find our value at point 2. So if we go down here and scroll down, just get that all set up. Okay, so if I take you down to here and we go moments at point 2. So imagine we're making a cut in the beam at point 2, and it is pinned here. So what do we have going on to the left hand side of point 2? We've got a point load of 5.625, and we also have our line load of 3 kilonewtons per meter. And this distance here is what we calculated from our x in the shear force diagram, and that is, I've actually forgotten what that was. X is 1.85 meters along, so 1.5 meters. So if we look at this equation and we assume everything going clockwise is positive and any forces pushing us down anti-clockwise is negative, we get this. So we've got 5.625 kilonewtons times 1.85 meters. Take away 3 kilonewton meter line load times by 1.85 meters, and then times the centroid of that, because that force is acting at the centroid of that line load. So 1.85 divided by 2, 0.925 meters. That equals out to 5.625 times 1.85, take away 3 times 1.85 times 0.925 gives us a crazy long number, but we're going to round it, so it's going to be 5.27 meters. So we know our moment up here is going to be 5.27. That's parabolic going up. So between point 2 and 3, if we look at the shear force diagram, it's in the negative axis and it's linear, so we know our bending moment is going to be parabolically decreasing. So it's going to decrease to around here, but we want to know what value this is at point 3. So like we've done for point 2, we're going to make an imaginary cut, and then we're going to take everything which is on the left hand side of point 3 and imagine it's a hinge. So we've got this, and then we're going to have 3 meter line load, and this is 5.625, and this is 3 kilonewtons per meter, and this is the distance on the left hand side is going to be 2 meters. So if we write out our equation for, let's just box all that off, we go from 3 is 5.625 times 2 meters, take away 3 kilonewtons per meter times 2 meters times 1 meter, because that's a lever arm from the centroid of the line load. Punch that into our calculator. Gives us 5.25 kilonewton meters. So that's our value here, 5.25. Oh, let me just go to that. There we go. And that's starting to look about right. So our next move is between point 3 and point 4. So if we go back to our shear force diagram, we've got a flat line. So that means our line's actually going to be linear between point 3 and point 4. So we want to find a value at point 4. Now point 4 is going to have 2 points on it. Because we've got a bending moment, we're going to have, like we would in a shear force diagram, we're going to have a point upper, and then we're going to have a point, and that could either go instantly higher or lower when you hit that bending moment diagram. So it's just going to jump up. So our first point is going to be us calculating the bending moment just before we hit that 2 kilonewton meter bending moment. So if we do the same as we have done before and just get all this out, at point 4, if we were to make a cut along there, that's point 4, we've got reaction force up of 5.625, and then we've got our line load of 3 kilonewtons per meter, and there's not enough room here, like that. That is acting 2 meters there, 2 meters there. So M4 is going to be 5.625 times 4 meter lever arm, and take away 3 kilonewton per meter line load times 2 meters times a 3 meter lever arm, and that's going to equal 4.5 kilonewton meters. So that's going to be about here, and that's going to be a linear line between point 3 and 4. And because, as I mentioned, we're going to have another point here, which is going to be from when we hit our 2 kilonewton meter moment, which is going to make us jump up. And because it's going in the clockwise direction, it's jumping up positively, so it takes us up an extra 2 kilonewtons per meter to this point here. So that's going to take us to 6.5, and this point down here is 4.5. So now between point 4 and 5, we're going to do exactly the same as we've done before, and this is actually going to be a linear decrease. So I'm just going to quickly write out what we would expect to find for M5. So we've got our 5.625 reaction over here, and that's acting at a total of 7 meters away. 7 meters. And then we've got our negative moment from our 3 kilonewton meter line load. So that's 3 kilonewtons, and it's acting over a total of 2 meters. And that's lever arm is 3 meters plus 2 meters, 5 meters plus 1 meter, 6 meters. And then we've also got our positive 2 kilonewton per meter moment acting on the left hand side of our cut. So we add that in, and that gives us a total of 5.625 times 7 minus 3 times 2 times 6 plus 2, 5.375 kilonewton meters. So that looks to about here, and that's 5.375, and that's decreasing linearly there. Between 0.5 and 6, we're going to make a cut at 6 and take everything to the left hand side of it as before. So I'm running out of space, so I'm just gonna move this around slightly. So here, so M6, I'm just going to do this here. So as for 5.625 reaction times 8 meters this time, we've got our 3 kilonewton line load acting over 2 meters, acting at a lever arm of 7 meters this time. You guys are starting to get the picture now, hopefully. We've then also got this is going to be negative. We've got our positive 2 kilonewton per meter bending moment, and then we've also got a 5 kilonewton point load, which is going to be one to make us rotate around anti-clockwise, 5 kilonewtons, and that's acting at a lever arm of 1 meter away from our support. And if we equal that all out, we should hopefully get 0. And if we don't, that means we've made a mistake somewhere. I have, you haven't. -5, and we get 0. 0 kilonewtons per meter. So put this down here. And this should be this looks a bit janky, our bending moment diagram. It should be drawn out if it was drawn out accurately. It should be more smooth, and this line would actually be more linear. It'd make a lot more sense. But this is the bending moment diagram, and we've already calculated the shear force diagram. I hope this helped. If you enjoyed the video, or if you found any mistakes, let me know in the comments. If you have any questions, just either direct message me or leave a comment below. Yeah, and if you like the video and would like to look out for more content, please subscribe. I should have some more example videos coming out soon, so I hope this helped.